Cool. So good afternoon, everybody. We'll start now this second lecture on our model of deep learning for artificial intelligence. So this first lecture is gonna cover the Perceptron. So I'll start sharing the screen first, and we'll go through these slides. Great. So you got it now. So first, I will acknowledge Santiago Pascual and Kay McGuinness for helping in setting up this this lecture, and actually the other ones that we'll cover today, because today we're going to cover 4 modules. And actually, if you want to watch like some of our previous lectures on topic, you can just go and see those videos that we have publicly available. So what I will do for this topic first, I will first explain how, by combining the concepts of regression and classification, we can solve a simple problem, which is called binary classification. Binary classification is a task in which we want to decide between 2 classes, right? Between cats or dogs, for example, or actually, I think we're going to be working with class 0 or class 1, or cats and dogs. And we're going to solve this task in a very step-by-step manner. So first, I will explain how linear regression can help in that. Then I will combine it in something called logistic regression. I will explain what logistic regression means, and then how we can solve a classification problem by combining logistic regression and something called the decision threshold. Then once these problems have been defined, later I will explain like the perceptron, which is the goal of this talk, and explain how this very simple architecture can be used to solve this problem. Let's start with linear regression. So as you saw in the previous lecture, linear regression would be like probably the most basic task in machine learning, in which what we have is some input variable. In this case, it's 1D. You already saw it from the previous lecture. And some training samples. You have here these points in green. And what we want to do is estimate the parameters of a line. So that would be the slope and the bias, so that whenever we have any x value, we can map it into the predicted labels y, following a linear rule. Okay, so training this kind of model would be learning or estimating the parameters, in this case w and b. So it will be like 2 parameters, 2 scalars in this very, very simple example. So if you want to do that coding, because you will soon be using coding PyTorch for this task, you can just basically do it with a very simple call called linear, a linear layer, in which you will need, in this case, this example has like, what if my input has 1, 2, 3 dimensions, this example. So here you the dimension of the input, and then at the output, in this case, will be like only 1 single value, y, so 1 dimensional. These are the things that you will be doing further in the course, right? So this PyTorch has a way to later estimate the parameters that we'll cover later. So nothing new now, or not much new. I already explained the idea of linear regression from the previous lecture when I was talking about the prices of houses, if you remember. Okay, now how can we, let's assume that we can solve that we can solve linear regression from our data, but let's see how can we use that to move it to solve a classification problem. So let's follow the example. Imagine that what we have is a set of images of cats and dogs, actually puppies and kittens, and that somehow, magically, we have a feature extractor that maps each of these images, which will be like 2D in the sense of space, plus 3D in the sense of RGB pixels. So it's a set of 3 arrays of 2D arrays. But somehow you do some magic there that we will cover in the future, so that it maps each of this image into an axis. Okay, we will call it X later. in such a way that notice that so if we follow this axis, there is an order in the sense that there's a cat, 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 dog, dog, right? So these images that they were in this representation shuffled, right, in this 2D projection that I put on the slides by chance. It would be great if we had some magic tool that would map them into a way that if each of the image was a scalar or a 1D number, that the order of this scalar would leave at one side the cats and the dogs on the other side. That would be awesome, right? That would be great. And actually, that's basically what deep neural networks do in the end. Okay, normally they don't map into a 1D. That's super simple. That's great to do the example, but okay, nothing prevents you from doing that. You can try to map images of cats and dogs into a single scalar and see if you can solve that. So in future lectures, we will deal with this magic here, but not today. Okay, now let's assume that we have that and that we have this mapping. Okay, the idea is, again, is like more or less the value that you have here mapped. It's of the cats and the dogs. This will be X. Was deleted, but there should be an X here. Okay, now next step. Now on our X representation that was removed, I think I will add it because it's going to help. So we have some linear regression module that will map them in a following. Just notice what's happening there with the linear regression. What's happening here now is that I'm moving, or I'm projecting all the cats into this, so below 0, and in the way like all the dogs, they are in a over 0. So you can think that linear regression is like a linear projection. Okay, so actually here we can think that it's something like this, right? That it's kind of shifting the data of this data on this side. So it's kind of moving the cats below 0. And that's something that you can do without linear regression. With the slope and all that, you can play with that. So, and that's something that you already know how to do, or that's what I explained earlier. But remember the headline that you have on top that says, okay, here what we want to do is to go from regression to classification, because now what I have is like in one side of, let's say, in the sign, negative values of my scalar. Now it's called A. I changed from X to A. Negative values correspond to cats. Positive values correspond to dogs. But I still want to solve a classification problem. Classification problem, it's not, let's say, it's not simply higher or lower than some value. I want at the end some label for cats and for dogs in a numerical way, because we are trying to encode everything in a numerical way. Okay, so I think that's the wrong question. Okay, sorry, I made the problem editing. So how can we? Oh, no, it's correct. How can we, from these values that you have here, the output of the linear regression, how could we change them in such a way that the output will be 0, so that we would map the cats into a 0 value and the dogs into a 1 value. So now we want to assign a numerical value to the cats and to the dogs, which is going to be the class 0 for cats and class 1, so value 1 for dogs. What function do you know that would allow you to do this mapping? And now it's turn for you to answer on the chat. So what function do you know? Okay, thank you. So was a prompt answer that says the step function could do that. And if you have done especially telecommunication engineering, you have done quite a lot of that, right? This is the step function. Or maybe you have known it as the Heaviside function. But basically what it does is like it maps all negative values to 0, all positive values to 1. So that's great, because this step function allows us to map from 0 to 1. This reasoning that I have done in 1D Normally, if you read the textbooks, you see it on 2D, which I think it's a bit harder to understand, but it's exactly the same story. So now imagine that your input data, your X, is not one-dimensional, but it's two-dimensional. I think the other day we talked about the weight and the age, right, of the animal, and we thought that, said, okay, maybe somehow if you can draw a line between the samples, it will be possible to manage to classify between cats and dogs. Again, that's the same story. Now in a 2D space, you can think about that 2D slope or heaviside, and that's what you are going to be solving. If you can orientate the slope in the right way, or actually orientate the data in the way that the slope 2D slope will map between 0 and 1, you're gonna be solving again the class problem of mapping. In this case, could be cats into zeros and dogs into ones. Cool. So this is great. If we had the heaviside function, that we can solve this classification problem. But actually, we are not going to be using the heaviside function. So actually, later in the next module, you will see that this heaviside function has a problem, which is that it's flat, okay, in almost, so it's flat in most of its range, right, and most of its values, and actually it's not derivative around 0. And this is a problem because later in the next lecture you'll see that when we build deep neural networks, we're going to be running an algorithm called backpropagation that will require computing the derivative of all the functions in the network. So this is one of the reasons why the heaviside function, we will not be able to use it in our case. Okay, we can use it, of course, when you are not trying to do backpropagation, and it's kind of the obvious thing to do. But we will not going to be suitable for our problems. In our case, what we are going to be doing is using kind of a soft approximation of the heaviside function. So we'll still be trying to map our values between 0 and 1, but we're going to be using something called the sigmoid function that probably maybe you know about it already, and if not, I'm defining it here. It's a function that goes between 0 and 1. It's centered around 0, like the heaviside step function, and this is its formulation. Okay, this is a sigmoid function, and we're going to be using it quite a lot especially when trying to solve classification problems combined with a regression or linear regression model. This same reasoning that here I applied in 2D input signals, you can apply it to 2D, right? So here, if your input features, they were 2D, here I have drawn, or actually Santi, draw this 2D sigmoid that you can think that it's mapping all the values which are over here into the red class, and all the values on this area into the 0 value, the 0 class. And actually, one of your first labs you will be doing is learning the parameters of this sigmoid so that it can solve a classification problem starting from a logistic regression. Okay, so here we have the logistic regression that's mapping. Something that is important is that this logistic regression, it tends to 0, it tends to 1, but it never gets there. Okay, so it's not here. These values are not exactly 1, and this slope here is not exactly 0. So there's some slope always. It's continuous. The most of our slope is here, and actually, when we are training our networks, you will see that they will train well if we are in this area. Where in this area it acts kind of a linear function, but what is interesting is that it never gets 0, but there's always some slope, and it never gets to 1, and there is always some slope. So it can always provide gradients when training. You want to do that with PyTorch. Also, you will do this in one of the labs. What you will be doing is you'll be having first a linear layer that will be the linear regression, and on top you will add a sigmoid activation. And now notice that the outputs are bounded between 0 and 1. Next step, as this is not exactly reaching 0 or 1, how can we take the final step to make it like class 0 or class 1? So that's kind of easy-ish to do. We can just directly set a threshold, right? So when we have our sigmoid values, we can take a decision, okay, class 1 will be all values that, for example, that in the sigmoid, they are over 0.5. That's kind of the, you would say that all the samples which are located here that will map into the sigmoid, into this mapping, you say this is going to be class 1, and all the samples that you have here, that if you map them into the sigmoid, they would match over here. You said all the values under the threshold, below the threshold, they are class 0. And now that you set the threshold, is the moment in which we are really assigning a class label after the sigmoid. So in the end, it's like doing what we were doing with the step function, but now we make it softer, or we apply a soft solution that will allow us later to compute gradients and estimate the parameters of our, in this case, of our linear projection. So in the end, you'll see that when we train neural networks, we are actually estimating these W's and this D. There is, actually, I said that we can set the threshold to 0.5, but actually that's a convention. It's totally up to you, right? So the decision threshold can be 0.5, but it can be whatever you want. You can move it to whatever value you want as a threshold. Just take into account that if you set a higher threshold, what will happen is that your precision metric will increase. The precision is a metric that says like which is the rate or the percentage of detections of let's say if you are trying to detect dogs. So if you want to make sure that when you detect the dog, it's actually a dog. You don't want a false positive. It's a way to have a high threshold. But on the other hand, if your threshold is lower, then maybe you will get like all the dogs that you had before, but maybe some cats will also be now detected as dogs. But your precision will decrease, but the recall will increase. So recall means like what percentage of the samples that you wanted to detect, say of all the dogs you wanted to detect, which percentage did you actually detect? Yeah, if you found all of them or you missed some of them. So high recall means that you didn't miss many of them. And there's a trade-off, right? So if you increase the decision threshold, you're going to be harder to decide. It's going to be harder to decide that that's a dog. You're going to be more confident, but then maybe you might be leaving some dogs out. So maybe then your recall may decrease. So that's a classic trade-off in machine learning on the decision thresholds, and it's something that in the end you'll be able to decide. So in case you never heard about all these problems of how to deal with precision recall, I suggest that you look at this chart, right, in which this would be like the ground truth, right? Like if you say you are not pregnant, so this is a man, so he cannot be pregnant. So if the doctor says it's true negative, so that's a prediction that will be correct. It's a true negative. But if the doctor says that you are pregnant, as it's a man, the prediction here is wrong. So that's going to be a false positive. And on the other hand, if you see this lady who is obviously pregnant, and the doctor says that you are not pregnant, then so the lady is pregnant. If the prediction is that it's not pregnant, then that becomes a false negative. And on the other hand, if the doctor says you're pregnant, which is correct, that would be a true positive. Okay, so this kind of trade-off and concepts are quite common in machine learning. So now that I presented the problems, how you can solve a binary classification problem like combining concepts of regression, linear, logistic regressions, and decision threshold. Let's see how the perceptron, which is going to be the basic unit we'll be working on, can manage them, can handle these tasks that I just introduced. So let's look at the architecture. What does a perceptron look like? So the perceptron is actually the basic unit of deep neural networks, and can be seen as an analogy of a biological neuron. So biological neurons, what they do is they fire an impulse once the sum or the sum of all the inputs is over a threshold. So it has some stimulus, they trigger. Okay, it's kind of a switch. And this analogy of a biological neuron, that's what inspires the perceptron that we're going to be looking at, which was proposed by Rosenblatt in 1958. So how does it work? We're going to have an input. In this case, we have an input of dimension 3 and the corresponding weights. In addition, a bias. Finally, an activation function, and that's going to be the output of the perceptron. So this is a perceptron. That's the basic unit that, or the most generic scheme for a perceptron. The behavior of the perceptron is modeled by the weights that we have here and the bias. So these values are the values that we are going to be estimating when we train our models. Notice that after this first stage, before the activation function, what we have is a linear combination of the input. Here it's a vectorial notation, so the weights multiplied by the vector plus a bias. Okay, so this I guess that you can already see that it's in the end this is a linear. This part of the model solves you can think that it's solving a linear regression. Later, there's another model called activation function that is going to introduce some nonlinearity in general, and that's one kind of what makes interesting connecting layers of perceptron. You'll see that we're going to be using many perceptrons in your network, and we are going to organize them on stacks of layers. And the idea of having stacks of layers, it's connecting or combining the behavior of this linear part of the perceptron with this part that, in general, it will not be linear. The perceptron can be used to solve both regression or classification problems. And actually, it kind of depends on what we put here in the activation function. So, for example, imagine that the activation function is the identity, which is equivalent to saying that there's no activation function. In this case, the linear combination that we have at this point, if this is just the identity, it's also the output. So the output, in this case, it's a linear regression. So in this scheme that you're seeing now, the perceptron is behaving as a linear regression. So this same architecture addressing this task of linear regression. What if now we don't have an identity as an activation function, but now we put as an activation function a sigmoid? Now, in this case, the output, actually, it will match the formulation of the logistic regression. So now our perceptron is solving a logistic regression problem. And as you saw in the previous slides, when we do logistic regression, is because later on we will actually, so we are trying to solve in the end a classification problem. We are trying that the output of our perceptron go to 0 to 1. That's why we introduced these sigmoid activation functions at the output. In this case, if you have this setup, just notice that before the activation function, this linear combination, that's what we are going to call the logits. It's a term that we're going to be using also quite often. Of course, as I just presented a few slides before, by having a a sigmoid as an activation function, or actually there are some others, but let's say a sigmoid as an activation function and a threshold, we can solve binary classification problems with a single perceptron. Okay, so with a single perceptron, we can solve linear regression problems, logistic regression problems, and binary classification problems. And I noticed that actually the logistic regression is typically like the step before solving a binary classification problem. So if you want, you can think that it's the same one, the same task. When I presented the architecture, there was a block that I called activation functions, and I presented 2 activation functions so far, or 1.5 if you want. Do you remember which activation function did I discuss so far for the perceptron? Can you write them on the chat? So which activation functions? Okay, the sigmoid, right, for the logistic regression. Okay, step function and sigmoid. Cool. Yeah. Actually, okay, I guess it's fine. Yeah, okay, that's fine. I was actually more expecting like one activation function, which actually it's not activation function. When I was talking about the perceptron, was the identity, but I think it's good that it provides better your answers about step function and sigmoid. So basically these 2 activation functions. Then, oops, there might be other functions that I use in deep neural networks which are not sigmoids or step function. And notice that step function, in general, we will not be using it because it's not differentiable, and that will prevent us from training the parameters, as you will see later. Okay, so in general, there are a range of functions that, of course, you can imagine any nonlinear function, but some of them, they are more interesting when dealing with deep neural networks. Normally, we will want functions which are mostly smooth, continuous, differentiable, fairly linear, and that's why typically we have the sigmoid, the tangent hyperbolic, the parabolic tangent, and the ReLU. Okay, so actually the ReLU, it means rectified linear unit, and it's a function that you're going to use it quite a lot because what it has, it's a 0 value for negative inputs, and for positive inputs, it will have just the identity as the output. Okay. 1 or 2 questions. What is the derivative of the ReLU based on this figure? Can you answer that also in the chat? Okay. So 1 is derivative of the ReLU for which range of input values? Cool. Yeah, for positive values. Okay, for positive values, the slope function is 1. And what about negative values? What's the slope of the ReLU for negative values? Yeah, the answer is correct. So for negative values, the derivative is 0, so it's totally flat. So there's no derivative. Okay, and I know that earlier I was, yeah, in 0 we have a problem there, but I would say that in practice we don't really care much about what's happening. You know, if you're mathematicians, I'm sure that you're very concerned, but in terms of engineering aspects, just don't worry about that. Okay, we can, I guess that in implementation, I'm not sure what the implementations are doing there, but whether you put a 1 or a 0, it will not change much the output of the training process that we'll be interested on. But that's a good point. Like what happens in the 0 when they put the 0. Okay. Here you have other popular activation functions. There's this hard sigma that it's linear near 0, but then it gets 0 or flat. Sorry, 1 flat when you go away from the origin. you have the liquid ReLU, which is it's kind of popular. The liquid ReLU it's for positive values. It has slope 1, and for negative values, it's not 0, but it's not. The slope is not as high as 1. It just there's a little bit of a slope, and you can decide which one it is. Then there's the hyperbolic tangent, which it kind of has a similar behavior as the sigmoid, but in this case, it moves between 1 and -1. And this LU, it's more exotic, I think. It's linear in this part, and it's non-linear when you move onto negative values. And that's a kind of, basically, you'll be using, most of the time you'll be using ReLUs, sigmoids, maybe tangent hyperbolics if your outputs of your model is between 1 and -1. Okay, now I give you some small exercise to do now. Okay, here I would like you to consider that we have a binary classifier that we implement with a single neuron with only one perceptron, as like the ones that you have seen so far, and with 2 weights. One of the weights is 0.2 and the other one is 0.8. And also there's a bias, which is a -1. And we consider that you have an activation function to be the sigmoid. Then first, I would like you to draw a schema of the model. Later, compute the output of the logistic regression for a given input. So here I'm giving you the input data for your model. And then finally, that you tell me that if we consider that the classification threshold is quite high, like 0.9, tell me to which class does this sample 1.1 belong to. Okay, so this will be, I would like you to do this now. And by the way, I will start the recording.